So we have a curve, right? Solving curves or equations can be difficult at times. If it's a quadratic, you already know how to do those, but they can get fairly complex. But a tangent line is a linear line, right? Yeah. Solving linear lines is easy. So you can use this thing called linear approximation that says, and we're going to develop it and show you how it works, that as long as I'm close to whatever this a value is here, I can use the tangent line to estimate other values. So I'll just call this x, call x1, x2. And this bit in here is going to be called delta x. Okay? Basically, it's the distance between x and a. All right? You can go on either side. You can see, as long as you stay fairly close to a, you're pretty close to what the actual value is. Okay? If you go really far away from a, you can see that value gets farther and farther away from the actual value. Okay? So, what's the equation of the tangent line? Well, if you go back to your grade 10 math, we can use the point slope equation, which is this. Remember that equation? No, you've never seen it before in your life. All right. So, the slope, m. Well, how do you find the slope of a point on a curve? We're in calculus. How would you do it? You're not wrong, but how would you do it if we're in calculus? It's the derivative, right? The derivative is the slope of the tangent line. So if I want the derivative at a, because I want the tangent line at a, I'm going to take the derivative of the function at a. Okay. I also, x1, y1, that's the point. On this graph, x1 is our a value, and y1 would be f of a. Does that make sense to everybody? No? X, X, Y, Y.
But x1's on the right of it.
Oh, okay, sorry. Let's just erase those. There you go.
Oh, okay. Nice.
I'm talking about this equation, sorry. That I see why that would confuse you. All I did is change out the point, because when using point slope, the point that you're putting in is x1, y1. That's what they call it.
Okay.
Sorry.
What did you change?
I just erased those. Just call them x. It doesn't matter. Call them xa, xb if you want. It doesn't actually matter. All I did is take slope. Instead of writing m, I'm going to rewrite it as the derivative at a. And instead of writing x1, y1, the point, this point right here, has coordinates a and f of a. Okay? So if I put that into our point slope equation, this thing, I'm going to get y m x minus a. So I've got that. And then I'm going to move over the f of a and get y is equal to f of a plus m x minus a. That's the formula for a tangent line. And where's not m, I don't want m. Why am I writing m? Don't write m, people. Write f prime of a. Because we're in calculus and we don't want to write m. I don't know why I wrote m. That's the equation of any tangent line on the graph at any point A. what we're going to do is we're going to use that to estimate other values. So the x, say I wanted to estimate this x value, and I know the actual value is on the graph right there. I'm going to use the tangent line equation to get there because I know it's close. Okay? So this x minus a is, you could call it delta x, but it's really just how far are you away from a? I don't know why I put that in quotes. So how far you are away from A. All right. So this, now look, you're not going to use this. You're going to use a calculator. You would use a calculator nowadays, but this can be applied to anything. But we're going to use it for radicals because they're easy to work with. So find the cube root of 8.10. Okay, so this is our problem. We want to find the cube root of 8.10 to like 3 decimal places. Actually, we'll go 5 decimal places. So way back when, before there was calculators, this is what you had to do. Okay, so what is our function? What function is this? It's the no. Just tell me what the function is. It's a cube root function, right? Not a cubic, cube root. It's a cube root function. It's this, which is x to the 1/3. That's the function you're dealing with because you're cube rooting 8.1. Okay. So what is our a value? So this is what you want to pick. The a value is a point that you know. What is the closest perfect cube that you know that's close to 8.1? 8. All right. So pick a that is close to 8.1. And it's a perfect cube. So we're going to say a is equal to 8. Okay. All right. So if you look at the formula here, it's f of a. Okay. Well, f of x, it's a cube root. So it's cube root of 8. What's the cube root of 8? 2. That one we know. We have to do the derivative. What's the derivative of a cube root? X to the 1/3. To the negative 2/3. Now, it's f prime of a. It's this number that we're trying to find. So we got to put a into our derivative. So f prime of a, or sorry, of 8 is going to be 1/3 times 1/8 to the 2/3. Does everybody understand where I got 1/8 to the 2/3 from? I put 8 into here, right? And because it's negative, it flips it down and to the power of 2/3. Yes?
Yeah.
Okay. What's the cube root of 8? 2. 2 squared is 4. So this bit is 1/4, right? Times 1/3 is 1/12. Okay. Now we're basically putting it into this formula right here. So we're going to say the cube root of 8.1 is approximately f of a is 2, plus the derivative, the value of the derivative at a, which we just said is 1 over 12. And then this is the distance. So x, this is our x value, the actual value you're trying to solve. So 8.1 minus our a value, which we said was 8. That's 0.1, right? Do you want to do this with fractions? We'll do decimals in a sec. So 0.1 is 1 over 10. Yeah. Times 1 over 12 is 1 over 120. People love fractions, don't they? Yeah. Times 1 over 12. Does that make sense? Okay. If you do a common denominator, you're going to get 240 over 120 plus 1 over 120, which is 241 over 120. And what the heck number is that? Way back when, you could do long division. We're just going to put it into a calculator. What's 241 divided by 120? So 5 decimal places. 2.0083.
Doesn't this kind of defeat the purpose because we're using that?
No, you would have done it. And for complex things, you're not doing it for square roots. I'm not going to, in real life, you're not going to do this. It's the idea that you have to understand, that you can use linear approximation to solve complex issues. Okay, 2.0083. What's the actual if you did the cube root of 8.1? Eight, 2, 9. So we basically got the same, first 3 decimal places were the same. Okay, just by using a linear line instead of doing the curve. Okay, now you can apply this to a lot of different things, as long as the thing is you have to be close to the point you're talking about. So for example, we're just going to do one more. If we did, we'll do a cube root, but we'll do cube root of 25. And say we used 8 as our a value still for this one. Now that's very far away. It doesn't make any sense, but just say we did. Say we said a is equal to 8. Okay. All the other numbers are the same. This is the same. That's the same. The only difference is going to be this number right here, this x minus a, this thing. So if we put it into the formula, we would get 2 plus 1 over 12, 25 minus 8. Which is going to be 2 plus 1.416, which is going to give us 3.416. What's the actual cube root of 25? Yeah, 2.9240. So this is the actual, that's what we got. Why is ours so far off? You didn't use one that was close, and if you look at it visually on the graph, we picked one way out here. So there's the actual value, and that's the value we got. You can see the difference gets bigger. The further you move away from your point, the less accurate you're going to be. Okay? So that's why you have to be, quote unquote, near your value. All right? But over small distances, you can use the linear approximation, which makes solving things easier. If your function is super complex, you don't want to deal with that. You use a linear function because they're straightforward to solve. This formula is the same formula for every single question you use. You just figure out the derivative, you pick your a value, and you know the distance from your a value, which is that. That's it. I know you don't look very impressed, but it's a pretty cool idea. The fact that you don't need to use the actual function, you can use a linear function to approximate it. And at least for us, we were within 1,000th, 3 decimal places. I appreciate that. There wasn't a lot of motion behind it though. All right. 2, 3, 7. You're going to do 2 questions, 37 and 39, please. And the unit is over.